All right, example 5, again, is an open interval. It's an exponential case, the e function, and it's open because it's parentheses. The -2 and the +2 aren't a part of the function. It's open, meaning I can't plug 2 in because it doesn't exist there, or -2 because it doesn't exist there. All right, those would be open points. Everywhere else between them is fine, right, but does not exist at 2 and does not exist at -2. All right, so that means I want to find, hopefully, a critical value over that interval. So find my derivative and set it equal to 0. All right, so the 50 will zero out. The derivative of the exponential, well, this is going to require my chain rule. So first thing is the exponential. So I write down the original function as is. So 25e raised to the -0.4x squared. But then it's very important, key, that you don't forget the second half of this. The derivative of the inside, which is 2 times my -4, so I get -0.8x to the first. And then I will simplify that by multiplying my 25 and my -0.8 to give me -20x times the e term. Set it equal to 0. Now remember, the e term actually, this is never 0. So the only 0 I can actually get out is at the -20x. So -20x equals 0. Well, 0 divided by -20 is 0. And so that's the only critical value. And it is between my -2 and my +2. So it is on my interval -2 to 2. All right, so the test, in this case, in the open case, is using concavity. Which means I do need to find my second derivative because the concavity is found using the second derivative. That's why sometimes it's also called the second derivative test. Alright, so I got to go back up here. Actually, I'm going to write down my first derivative to find my second derivative. Alright, my first derivative was -20x e to the -0.4x squared. So I am going to have to use product rule and chain rule. First function, second function. So the -20x is my first. Derivative of the e, well, it's the same expression I had up there before. Right? The derivative of the e is itself, and then multiplied by the derivative of the inside, which is the -0.8, plus the second, times the derivative of the first, which is just the -20. Alright, so it's up to you. You can leave it that, because all you have to do is plug in your critical value. I'm going to clean it up a little bit, and I'm going to show you, just kind of always my rule of thumb is to clean it up. I'm actually going to pull out two things. I'm going to pull out the -20 and the e term. So I'm going to factor out -20e to the -4x squared. What's left over? Inside here is a -0.8x squared. And then when I pull everything out, remember I'm still left over with a 1, right? You factor everything out, you're still left over with a +1. It just makes it easier to plug my number in. All right, I'm going to plug my critical value in 0, right? My critical value is 0, so it's going to go in here into my second derivative. And so when I plug 0 in, that's going to come out 1. That's going to come out 1. All right, so I get left with -20. -20 means my second derivative is negative, so that tells me it's concave down at the 1 critical value on the domain, meaning it's this shape between -2 and +2. It has that shape concave down at the 1 stopping point, which means that has to be my maximum. Since it's the only place it turns, it's the absolute maximum. All right, so we have an absolute max at x equals 0 of, well, I've got to plug it in. I've got to go back in and plug my GH. Go back into my original function, plug in 0. So I go all the way back up here, plug in 0. That's going to become 1. 50 plus 27. So that's coincidence. It's also 75. All right, 75 is my absolute max. There is no absolute minimum. Doesn't exist, right? Doesn't exist at the 2, so those aren't minimums. Right? There's just a maximum in that case. All right, one more of these examples, and then we'll get to applications. So the last one's a logarithmic example, which we'll get to in the next video.